So in this part, we will discuss the continuous random variables. There are three types of continuous random variables that we discuss in this course. The first couple are the uniform and the exponential distribution, and then in a separate lecture, we will also discuss the normal distribution. As usual, we'll try to discuss the occurrences of those random variables and then the properties of the random variable. So when the random variable appears in the continuous case, and the other thing is how its probability density function looks like, how you can get the mean and the variance for the random variable. So starting with the continuous uniform distribution, it's not that much different from the discrete uniform distribution. In the continuous uniform distribution, typically the continuous random variable x has a range, continuous range of values, starts with value A, finishes at value B, and in between, the probability density function is a constant value, which means that if you move a constant distance, you will get a linear increase of the area, right? So the area under the curve is the integral under the curve. And if you move a certain distance here, then the area is the height multiplied by the width, because it's going to look like a rectangle, right? So basically, probabilities between two values that have the same separation distance are going to be exactly the same. So the probability that, for example, x is greater than 3 less than 5, so here we have a range of 2, is going to be equal to the probability that x is greater than 5 less than 7, which will also have a range or a width equal to 2, right? So that's why it's a uniform distribution. There is no reason. When is this used? It's used in the case where there is no reason to believe that some values of the continuous random variable are more probable to occur than other values, or some ranges of the random variable, the continuous random variable x, do not have any reason to be more probable than any other range. Now, given that the random variable x starts at the value A, finishes at the value B, and the value of the probability density function small f of x is a constant value, then it must be that, as we know, the total area under this curve, which is the total probability, should be equal to 1. So if we know that this width is b minus a, then this height must be 1 over b minus a, such that when you multiply the width by the height, it's going to give you the area of this rectangle, the total area under the curve, which should be equal to 1. So immediately, once you are given the values of a and b, the start and the end range of the random variable x, you can figure out the value of the distribution. F of x is equal to 1 over b minus a, and this is only when x is greater than a, less than b. Right? For this type of random variable, the mu, the expected value, is equal to the start plus the end divided by 2, so a plus b over 2, and the variance of the random variable is equal to the end minus the start, so b minus a squared over 12. You can derive these equations from the definition of the mean and the variance, knowing the distribution, but we are not going to do this as usual. You just need to know how to use these formulas. So a uniform continuous random variable is completely defined once you know the a and the b. Right? So keep that in mind. Now let's take an example on a continuous uniform random variable. In this example, the random variable x has a continuous uniform distribution on the range from 4.9 to 5.1. Then the probability density function in that case is going to be equal to 1. So f of x is equal to 1 over b minus a, as we learned before. So this is going to be 1 over, what's b? 5.1. What's a? 4.9, right? So it's equal to 1 over 0.2, which is equal to 5, right? And that's what we see here. So f of x is equal to 5 when x is greater than 4.9, less than 5.1. And if you want to draw that and this is how it looks like. Okay, so 4.9 up to 5.1. Now, what's the question says, what's the probability that a measurement of current is between, so this represents the current in a particular circuit. What's the probability that the current is between 4.95 and 5? So in this case, this probability by definition is equal to the integral, okay, over the probability density function from the start value until the end value. So it's between 4.95 up to 5. So it's from 4.95 to 5. And the value here is going to be 0.25. If you want to calculate the mean and the variance for this random variable, then the mean, mu, is equal to A plus B over 2, which is equal to 4.9 plus 5.1 divided by 2, and that's equal to 10 over 2, which is 5. And that's what you see here, right? The variance, V of x, or sigma square, is equal to B minus A squared over 12. So this is equal to 5.1 minus 4.9 squared over 12, which is equal to 0.2 squared over 12, and that would give us approximately this value. Okay, and if you are looking for the standard deviation sigma, it's simply the root of sigma squared that we have calculated here. So it's the square root of this value. Okay, pretty simple, easy to deal with. Notice that there is nothing that prevents the value of f of x to be greater than 1. It can happen, but because the value of small f of x is not probability. What probability is the integration under the curve. So that integration under the curve, any particular area under the curve of the small f of x, has to be less than 1. Until you integrate the whole area, it's going to be equal to 1. Okay. Now, the next important distribution is the exponential distribution. Now, the exponential distribution occurs in a very particular case, which is basically the inter-arrival times or the intervals between Poisson arrivals. And we'll come to that in a minute. Before going to that particular relation between the exponential distribution and the Poisson distribution, let's first look at the exponential distribution itself and its properties. So the random variable x that equals the distance between successive counts of a Poisson process with a mean lambda greater than 0, that random variable, so that's the intervals or the inter-arrivals between Poisson arrival incidents, that random variable is an exponential distribution, and an exponential distribution with a parameter lambda has the expression small f of x is equal to lambda e to the minus lambda x. Okay. And this is true for any value of x greater than or equal to 0 up to infinity. Okay. Now for that, again, if you draw that exponential distribution, you will see that at x equals 0, it's gonna be lambda times 1, right? So it will have the value, this is f of x, lambda here, and this is x, and then it will be a decaying exponential as x increases, right? So it will decay as x increases. That's how it would look like. Okay. Now for that particular continuous random variable, the expected value, mu, is equal to 1 over lambda, where lambda is the parameter of the exponential distribution, and the variance, v of x, is equal to 1 over lambda square. Again, you can calculate those from definitions, but you're not required to do so. You can just use the expressions directly. So the exponential distribution is defined completely once you know its parameter lambda. Now, what's this parameter lambda? It's 1 over the expected value of the exponential distribution. So if you know lambda, the expected value of the exponential distribution is 1 over lambda directly. Okay. Now let's elaborate a little bit on that relation between the exponential distribution and the Poisson distribution. But let's first try to solve this problem that we see here, and then we will do that elaboration. In a large corporate computer network, user logons to the system can be modeled as a Poisson distribution, Poisson process, with a mean of 25 logons per hour. What's the probability that there are no logons in an interval of 6 minutes? So here we are looking at the probability that within 6 minutes we have no logons. Okay. Now, if you want to solve this problem directly from the Poisson distribution, because it talks about a Poisson distribution where the mean lambda of this Poisson is equal to 25. So lambda is equal to 25 per hour, right? And remember that the expression for the Poisson distribution, the probability of X number of arrivals is equal to lambda t to the power X e to the minus lambda t divided by factorial X, right? This is the probability mass function. Remember that the Poisson distribution is a discrete random variable. Okay, so now we are doing something related to the previous part, the discrete random variables, right? This probability mass function is defined as we see it here. We know the lambda, we know the duration, right? And the question is, what's the probability that there are no logons? So X equals 0. So we are looking for the probability that X is equal to 0 in interval 6 minutes. Now again, this is in minutes, but lambda is per hour, so we have to convert this interval t is equal to 6 over 60, which is equal to 0.1 hour, right? And then substitute this value, substitute the value of the t in the expression, and we are looking for X equals 0. So the probability of 0 arrivals within, so no logons means that the number of logons is equal to 0, which means that we are looking for the probability of 0. This is equal to, right, to the power X equals 0. So lambda is 25 times 0.1 to the power 0 multiplied by e to the minus 25 times 0.1 divided by factorial 0, right? This is equal to 1. This to the power 0 is equal to 1. So we end up with e to the minus 2.5, which is going to be equal to this number, 0.082. Now that's one way to solve the problem, right? Problem is about Poisson distribution. Now, how we can solve this problem using the exponential distribution that we have just discussed. Now, before doing that, let me describe that relation that says when does the exponential distribution appear. Remember, the Poisson distribution was talking about random arrivals, so arrivals that happens randomly, right? Okay, at certain locations. And then we were saying that within a particular interval, right? This is our interval t. What's the probability that the number of arrivals X is equal to a certain value, right? So we were looking for the probability that X is equal to some value. So what's the probability that X is equal to 0, like what we did in this example, or what's the probability that the number of arrivals within this interval is equal to 5, or equal to 6, or equal to 7, and so on. So those random arrivals, right? If you take a certain interval and count how many arrivals occur there, you will find a certain number. Leave the problem a little bit, come back, take the same interval, count, you will find a different number because it's random arrivals, right? Now, since these arrivals are random, then they occur, as we can see from the drawing, they occur at intervals, the distance between one arrival and the next one. This is called the interval or inter-arrival interval, right? The inter-arrival interval itself, as we can see, is random. Sometimes it's small, sometimes it's bigger, sometimes it's big. It can be anything, right? That's part of the random arrival occurrences, right? Now, those intervals are continuous because they are measured either in distance or in like time or whatever. So they are continuous and they are random. So they are continuous random variables. If the arrivals, the number of arrivals that we just discussed in the previous chapter, the discrete, the previous part of the discrete is Poisson, then these inter-arrival random variables, which are continuous, will follow an exponential distribution. Now remember that the Poisson, the only parameter that you know about it is lambda, the number of arrivals, the average number of arrivals in the interval, in a particular interval. Then this same lambda of the Poisson is the lambda that you used for the exponential distribution. So here, if we look at this problem, right? So that's the relation between the Poisson and the exponential random variable. So if we look at this problem and we want to solve it using the exponential, then the given to us is that, or the required from the given to us is that the arrivals are, so we start solving this problem saying that since arrival is Poisson, then okay, inter arrival is exponential continuous random variable, right? It's an exponential continuous random variable. And it has lambda equal to 25. So the same lambda that was used for the Poisson is the lambda that defines the exponential distribution. And remember that since lambda is 25 per hour, then our unit time in the exponential distribution is going to be hours. So any time that we use in the exponential distribution, right, x is going to be the time in that case, right, it's going to be measured in hours. So it depends on how lambda was defined. So it was defined per hour, right? Okay. Now, so remember that this is the inter-arrival. So it's the time between occurrence of one arrival and the next one. If we say that an interval of 6 minutes passes without arrival, the probability that there is no arrival within 6 minutes means that this is equivalent. So the probability that x is equal to 0 in 6 minutes, where x here is the number of arrivals, right? And that follows a Poisson distribution, is equivalent to the probability that this time t is greater than 6 minutes, because if the time between one arrival and the next is greater than 6 minutes, this is equivalent to the probability that a 6 minutes duration passes without any arrival. Any arrival will happen after that 6 minutes, right? That's the same equivalent. So now this t is our random variable as a exponential distribution because it's a time between one arrival and the next of Poisson process. So we are looking for the probability that x is greater than 6 over 60. Don't forget that we have to measure our time. X now represents x now, in this case, represents the time, not the number of arrivals, okay? I'm just using the same name twice, once to do the count, once to do the time. They should be different, but because we are using x as the time between arrivals, so I'm going to use x again. So the probability that x is greater than this value in hours. Don't forget we have to convert it in hours. So this is the probability that x is greater than 0.1 hour, which is from an exponential distribution because that time between one arrival and the next one, x, is an exponential distribution, as we have just explained here, because it's inter-arrival between two Poisson occurrences. So this is equal to, go for the expression, lambda e to the minus lambda x, and you integrate from 0 up to 0.1 with dx. And what's your lambda? Your lambda is the 25 value that you have here. Then you solve that, and you should get exactly the same value, 0.082, right? So we have seen here the relation, and we have shown also that you can solve these kind of problems that talks about the probability of 0 arrivals in a certain interval where the arrivals follow the Poisson. It can be solved either from the Poisson distribution as we did here, or it can be solved from the exponential distribution as we did here, because of the relation between the Poisson and the exponential distribution, right? So the remaining part here is just solving the problem in other ways. So the question here is, what's the probability that the number of arrivals is greater than a certain value, less than a certain value, and it tries to solve it using minutes. So basically it just tries to solve this in different units. So we have solved it in the hours. You can also convert everything into a per minute and work that out. The other thing is there is an important property that happens in the Poisson exponential distribution, which is called the memoryless property. And we'll discuss this in a minute after going quickly over the numeric example that we see here. So now we are looking at what's the probability that the time until the next logon is between 2 and 3 minutes. So now we are looking at, so if one logon occurs, what's the probability that the time until the next logon is between 2 and 3 minutes. So we are looking for the probability that x is greater than 2, less than 3, and that time between logons follows an exponential distribution, right? So you can either solve this by saying over 60, and you work this in hours, or as done in the example here, you convert everything to a per minute and you solve. Now the example here uses the hours directly. So x greater than 2 over 60, less than 3 over 60, and the way you get that probability is simply by integrating from the start to the end point, right? F of x is equal to lambda e to the minus lambda x, and x is greater than or equal to 0. That's the exponential distribution, and you want the probability that this random variable x is greater than this value, less than this value, right? So simply an integration. Now the next one says determine the interval of time such that the probability that no logons occurs in the interval is 0.9. Remember, we have done that using the Poisson distribution before. In this case, you can also do this using the exponential distribution. So for the Poisson, you were looking for, you know, the probability that x is equal to 0 is this value. And your unknown is the interval t, right? And then we have solved an example similar to that in the case of the Poisson distribution. The other way is the probability that x is greater than some unknown interval x, which is the interval between one arrival and the next, is equal to 0.9. And that probability calculated, if you want to calculate that probability, then it's, since your random variable is greater than this unknown value, so we are talking about the integral from x to infinity, lambda e to the minus lambda u du, and we use u here just because we have x in the integral, right? So x is greater than this value, so it's from this value up to infinity, and this is our distribution, the exponential distribution, which is the distribution that describes the time. So if you solve this integral with the lambda that we have here, you should get exactly this expression. And this is equal to 0.9. So now you solve for x, and by that you can find that interval that was required here. So you can solve it also from the exponential distribution. Again, you have one arrival, you have the next one. You want the probability that this interval is greater than some value to guarantee that within this interval no arrivals occur, right? And then you solve for that value, which is unknown to you at this point, right? The mean time until the next logon, so you have one logon, you have the next one. This is the inter-arrival time, which is random. What's the average of this value between one and the next? So of course, sometimes it's small, sometimes it's large. You take all these and you calculate their average. This is going to be the expected value of the exponential distribution, right? Again, because this value follows an exponential distribution, so mu is equal to 1 over lambda, as we know for the exponential, is going to be 1 over 25. And the variance of that is going to be 1 over lambda squared, so 1 over 25 squared. And then if you want the standard deviation, it's the root of that, which is 1 over 25, right? So direct. A memoryless property, the memoryless property that I discussed earlier for exponential distributions means that the memoryless property, okay, for exponential distribution means that
of the random variable x less than the value b, given that the random variable x is greater than the value a, is equal to the probability that the random variable x is less than the difference between b and a, so b minus a. So simply, the memoryless property means that the probability for waiting for a certain duration until the next event happens is equal, given that you have been waiting for a long time, is the same as the probability for the event to happen in the next duration, given that you have not been waiting at all. So basically, the exponential distribution, the memoryless property, forgets about the past, right? So that means the time that you have been waiting does not really affect the probability to wait for a certain duration. Now let's look at the problem. Let x denote the time between detections of a particle with a Jaeger counter, and assume that x has an exponential distribution with lambda equal to 1.4 minutes. So don't forget, lambda is equal to 1.4 minutes. I think this is wrong. It should be, the lambda is always number of occurrences per minute. Don't forget that this is the same as the lambda of the Poisson, as we discussed, that's the relation between exponential and Poisson. So it should be lambda equal to 1.4 per minute, right? So lambda is equal to 1.4 arrivals per minute, okay? And the important thing here is to notice basically that the unit of the duration for the average lambda is equal to 1.4, right? Sorry, the unit of the duration is equal to minutes, calculated in minutes. Now it says the probability that we detect a particle within 30 seconds of starting counter, okay, is equal to the probability that x is less than 0.5. So this is an unconditional situation, okay, and that can be calculated, right? So that's the probability that we start the counter, so we have not been waiting for any time. That's an unconditional probability. And then what's the probability that the next particle is going to arrive in 30 seconds? Now, again, we have to convert everything in minutes. That's why we say this is the probability that x is less than 0.5, because it's in minutes. And that probability can be calculated from the exponential distribution by integrating from 0 to 0.5 lambda e to the minus lambda x dx. And that integral, when you substitute with the lambda equal to 1.5, 1.4 per minute, then the it's e to the minus. Okay, so this I think the correct thing is that 1 over lambda is equal to 1.4. So because it's e to the minus lambda t, right? So the lambda here is equal to 1 over 1.4 minutes, and it's in units in minutes, okay? So again, just notice this error in the description of lambda. Now, in this calculation, all units are converted to, so we know that everything is converted to minutes. Now it asks you, suppose that we turn on the Jaeger counter and wait for 3 minutes without detecting any particle. What is the probability that a particle is detected in the next 30 seconds, so in the next half a minute again? So again, as you see in the diagram that I drew down there, we wait for 3 minutes, and then we are looking for the probability that we will encounter something in the next half a minute. So we will encounter something before 3.5, right? Given that we have been waiting for 3, so nothing occurred in the first 3 minutes. So we can write this probability as the probability that x is less than 3.5, given that it's greater than 3. How do you calculate this? Use the rule for the conditional probability. The probability of A given B is equal to the probability of A intersection B divided by the probability of B. Now, A is x less than 3.5, B x is greater than 3, so this becomes the intersection x greater than 3 less than 3.5, and the probability of A is the probability that x is greater than 3, right? So basically, this is how we get this formula. Now, those two probabilities, x greater than 3 less than 3.5, and the other probability x is greater than 3 can be calculated directly from the exponential distribution by doing the integration. The first one, integration from 3 to 3.5, and the other one in the denominator is from x greater than 3, so from 3 to infinity, right? The first integral can be calculated as we said, and it becomes 0.0035 as we see here. That's x greater than 3 less than 3.5. Then the second integral is going to be shown here, and that's the x greater than 3, that's the one in the denominator. The value here is 0.117. As we said, this is the integral from 3 to infinity, and it's calculated here also using the complement of from 0 to 3. So from 3 to infinity is the complement of from 0 to 3. So that's why it's written here this way. It'll give you the same results, right? Okay, now the remaining is to divide both of them to get that conditional probability, and we find that it is 0.3, which is exactly the same as the value that we got for the first part of this example, where we said we did not wait at all, and what's the probability that we encounter an occurrence within half a minute. It was exactly the same as waiting for 3 minutes and then encountering a particle in the coming half a minute, which is this conditional probability. The memoryless property has to be kept in mind that it is a property that exists in the continuous case for the exponential distribution. We did not discuss this earlier, but the same property exists for the geometric distribution in the discrete case. Keep this in mind, and by this we have finished the lecture for today. See you in the next lecture.